The first of these that we go through is Young's double slit experiment. So, in Young's double slit experiment, what our scientist Young did is he had a sheet, he cut 2 slits in it, and then he had a screen behind the sheet. This is what we can see here. We have the 2 slits and the screen behind the sheet. So, he shone light at the 2 slits and saw what he observed on the screen behind it. So, if light behaved as a particle, what we would expect is these 2 big blobs of particles behind the slit. It would kind of be like if you were, I'm not sure, like shooting a paintball gun through 2 big slits, right? You're not going to see particles over, you're not going to see paintball spiders over here or over here. You're just going to see big spiders behind the 2 slits, right? However, he observed something different. What he actually observed was a pattern, right? Where we kind of had bigger splotches over here, getting smaller and smaller on either side. And this is consistent with light being a wave, because we observed constructive and destructive interference patterns. So, this is a visual of what you can see. You can do Young's experiment very easily on your own. We have a bigger splotch here, and then it getting smaller and smaller symmetrically on either side. So, the waves of light interfere, making bright spots, and they interfere constructively yielding bright spots, or destructively yielding dark spots. So, Young's double slit experiment showed that light was a wave because the light exhibited constructive and destructive interference patterns, which is a property of waves. You would have gone through this in more detail at the end of year 11 if it feels a little bit familiar to you, but don't stress too much if you have forgotten a lot of it. The next thing you need to be able to understand is the wave model of light. So, the characteristics of electromagnetic radiation are that they consist of oscillating electric and magnetic fields. Oscillating means going back and forth, right? So we have electric and magnetic fields going back and forth. These 2 fields are at right angles to one another. And the speed of the wave is dependent on the magnetic and electric properties that it is traveling in. So the speed of light differs in different substances, which is called the refractive index. So of course, if you have a denser substance, there's going to be more resistance to the light, so it's going to take longer to travel. This is, an example of why on our Earth, right, when it's a sunny day, the air is warm. It's because the light is hitting the air particles and giving energy to the air particles, right? But in space, even though there's lots of light, right, because there's lots of light traveling through, it's a vacuum. So there's no particles for the light to actually hit, and nothing for the, to absorb that energy. So that's why it's so cold out there, right? Another example would be if you have a window facing the sun. Say you have a thick window. If you put your hand on the window, it might be quite hot, and that's because the light is hitting the window, and because the window is so dense, a lot of the energy is being given to the particles in the window and slowing that light down. Again, this is also why when we're talking about the speed of light, we usually refer to the speed of light in a vacuum, and that's because there's nothing to kind of interfere with the speed. right? Whereas if it's, just on Earth in general, the density of the air and, all this kind of stuff impacts the speed. And of course, because there's more stuff there, the speed of light is slower in the atmosphere than it is in a vacuum. All right. Now, these two oscillating fields are perpendicular to the direction of propagation. So as you can see, our wave is going in this direction, but our two fields are going up or across, right? Perpendicular to the direction. So this is the main thing that you need to remember about the wave model of light. The other formula that you need to remember is that the energy is equal to hf, where little h is Planck's constant. This number is in your formula sheet, so don't worry about remembering it. And f is the frequency of the light in hertz. Now getting on to blackbody radiation. So blackbody radiation provides evidence for the particle model of light, right? So blackbody radiation occurs when we have a black metal object that emits energy from within itself. And it does not reflect any light. So if you're giving it energy, it's not going to reflect any of it, it's just going to absorb all of it. Of course, there's no such thing as a perfect blackbody, but we can get pretty close. So, what we can see on the graph down below is the distribution between intensity and frequency. So as the frequency increases for the first part, the intensity increases, then as the this is the wavelength. As the wavelength increases, the intensity increases. As the wavelength decreases on this side, the intensity. So, hold on, I'm confusing myself. As the wavelength increases for this first part, the intensity increases. Then, as the wavelength gets even bigger, the intensity decreases. And obviously, these temperatures shown here, right? For the higher temperatures, we're going to have higher intensities. So, how did this show that light was a particle? So, the explanation of this kind of eluded scientists until a famous scientist, Max Planck, proposed that the energy emitted by black bodies was from the vibration of atoms limited to certain frequencies that were multiples of some value. So, light in this situation is emitted as packets or quanta. So the frequency of light emitted by the vibration of an atom is proportional to the change in energy of the atom, related by Planck's constant. So this is proof that light exists as a quanta. Alright. So the concept of blackbody radiation and how it shows that light exists as a particle rather than a wave actually gets a little bit complicated the more you dive into it. Kind of unlike the two other experiments that we look at, right? So what we have on the slide here is really enough, it's all that you need to know. If it seems a little bit confusing, that's because it is. When we get into Young's double slit experiment and then for the photoelectric effect, it's more easily understandable and you can go into more depth on them. The formulas that we have to describe blackbody radiation are E equals hf, C equals the wavelength multiplied by frequency, and then combining those two previous equations together, we get the energy is equal to hc over the wavelength. Alright. We also have Wien's displacement law, and this describes the relationship between the temperature and the peak wavelength of blackbody radiation curves. And this is given by the wavelength is equal to B, Ven's displacement constant, over the temperature in kelvins. Make sure that you remember that this temperature is in kelvins. It's really easy to be given a temperature in degrees Celsius and then forget to change it around. So, if you're ever asked to find the peak wavelength of the blackbody radiation curve, you can apply this formula here. Alrighty, so here we have a nice breakdown of all of the equations that you're going to need to be able to understand for quantum. So, remember the energy of a single quanta of light of frequency f is given by E equals hf, where h is Planck's constant, and that, remember, is in your formula sheet. The frequency and wavelength of light is related to its velocity c by the wave equation. That middle one isn't actually given to you on your formula sheet, but you are given v equals wavelength times frequency. So if you're having trouble remembering it, you can just remember that the velocity of light is c. So you can just sub in c for v. And then combining those two equations, we can get that the energy is equal to hc on the wavelength. All right. So this is kind of a visual representation of the photon model of light, right? So the photon model or particle model of light deals with the particular light behavior we observe of subatomic particles. So light exists as numerous particles which we call photons, and photons have no rest energy, they have no mass, and they have kinetic energy. So the energy of the photons can be described by E equals mc squared. Now the last kind of experimental evidence that we learn about when we're looking at the model of light is the photoelectric effect. So this one is particularly interesting. So the photoelectric effect provides evidence for the particle model of light. So when a metal surface is illuminated by electromagnetic radiation, essentially light, remember light is electromagnetic radiation, of a high frequency, electrons are ejected from the metal surface as a photocurrent. This ejection only occurs if the frequency exceeds the ejection frequency f0. The ejection frequency differs depending on the metal. So, essentially what we have so far is we have a metal surface, right? We have light being shone at this metal surface. If the frequency of the light is high enough, then the light is actually going to detach electrons from the metal, and these electrons are going to run around our electrical circuit to create a current, which we call photocurrent. However, if our frequency of the light is too low, then no electrons will be ejected. So, we observe some things about this experiment. Firstly, when a photocurrent is registered, increasing the intensity of light will increase the magnitude of photocurrent. So, the intensity is essentially how bright the light is, how much light there is. A good example of this would be if you are standing next to a street light, there'll be a greater intensity closer to the street light than farther away, because farther away the light has dissipated more, it's not as bright, right? So when the intensity is increased, when there's more light, it increases the magnitude of photocurrent. And then when we increase the frequency of the light after the ejection frequency, so once we've already got the electrons being ejected, if we still increase the frequency after that, that will increase the kinetic energy of the ejected electrons. Alright? So, increasing the intensity increases how many electrons there are. Increasing the frequency increases how much energy those electrons have. So, you can have a low intensity light with a high frequency that will eject not very many electrons, but all of these electrons will have a lot of energy. Similarly, you can have a high intensity light with a low frequency that will eject a lot of electrons, but none of these electrons will have a lot of energy. And then, of course, before we have reached our ejection frequency, it does not matter how intense the light is, no electrons will be emitted if we haven't reached the ejection frequency or the threshold frequency. Right? And then down there we just have a visualization. So we have the red light going in and ejecting the electrons from the metal. So, how does this prove that light is a particle? And why do we see all of this stuff occurring with the ejection frequency and the intensity of the light? Right? This is a little bit strange. What is the reason? So, this phenomena cannot be explained by the standard wave model of light. It can only be explained by the particle model. And this is because the only explanation is that a single photon ejects a single electron, giving all of its energy to the electron or none of it. So, think about it like this. If we had waves coming in, then the transfer of energy from waves would be continuous, right? Kind of the waves are coming in and giving more and more energy to the metal, and the longer the waves have been there, the more the energy will build up. So eventually, even if there is a low frequency, if there's a higher intensity, eventually that energy will build up and the electrons will jump off. Right? However, that is not what we see. What we actually see is that the energy of the electrons is equal to the energy given by the frequency minus the energy required for the electron to actually just jump out of the metal straight up, right? So what's actually happening is we have lots of little photons coming in here, and each of these photons gives energy to each of the electrons, but only one. Each photon gives all of its energy, or none of its energy, to each electron. The photon can't give some of its energy to one electron and some of its energy to another. No. All of its energy or none of its energy. Right? So, this makes sense then, right? Because if we have a higher frequency, our photons will have more energy and thus be able to give more energy to the electrons to bounce off. And if we have a higher intensity, we have a greater number of photons coming in. So if we have more photons, we have more photons to give energy to electrons. Right? If we have 1,000,000 photons, then 1,000,000 electrons can jump off the metal. However, even if we have a high intensity, we have lots of photons, but they don't have enough energy in themselves, still no electrons will be ejected because all of our photons are coming in, giving energy to lots of electrons, but they're not giving them enough energy. So what's happening is the electrons might be able to get a little bit farther away from the atom that they are orbiting, right? They might be able to jump up an energy state, which we'll get into when we get into standard model and quantum and the rest of quantum, but not quite enough to actually ionize the atom altogether and jump completely out of the atom, right? Only enough to maybe get it an energy state or two up away from the nucleus. All right. So, three forms of energy in the system can be defined. So the first is the energy of the photon, which is given by E equals hf. The second is the energy of the electron binding to the metal, which we call W, or the work function, which is given by H multiplied by the threshold or ejection frequency. Then we have the maximum kinetic energy of the ejected electrons. So our maximum kinetic energy is going to be however much energy the electron was given minus however much it took for it to just jump out of the metal, and that's what it's going to be left over with. And this gives us the maximum kinetic energy of the electron. The other thing that you need to be able to understand about the photoelectric effect is the cutoff voltage, or the stopping potential. So, what we can do is we can actually measure the photocurrent with a negatively charged collector plate. So, what we do here is the negative potential actually reflects the incident electrons, and eventually this potential becomes large enough to deflect the entire photocurrent, right? So the voltage that this happens at is actually called the cutoff voltage, or the stopping potential. Thus, the kinetic energy of the ejected electrons can also be determined by using our formula for kinetic energy, half mv squared, right? And this is going to be equal to our maximum kinetic energy and our cutoff voltage, right? Okay, now we're getting on to Rutherford and Bohr's model of the atom, which is our last part of quantum theory. So, Rutherford's model was the early model of the atom, not the earliest, but one of the early ones. And it's kind of the stereotypical model of the atom. So it describes the atom as mostly empty space, with a positively charged nucleus set in space, with negatively charged electrons orbiting around it. Right? So, there are actually limitations of Rutherford's model, reasons why it isn't so great. The main one is that Rutherford's model predicted that atoms would be super unstable, right? It predicted that atoms would actually collapse on within themselves, right? The reason that it did this is because we know that our electrons are moving around kind of in circular or ellipsoid orbits, right? But they're changing direction, which means they're accelerating. And we know that accelerating electrons lose energy. So, if these electrons are kind of constantly accelerating, constantly kind of like hemorrhaging energy, they're going to have less and less energy to kind of overcome the forces holding them to the nucleus. So as a result, they're going to collapse into the nucleus. So Rutherford's model predicted that our electrons would just kind of be like spiraling in towards the nucleus constantly, and all of the atoms around us would be super unstable, which isn't really what we observe, right? So, The other issue with his model was that he didn't specify where the electrons were. And this is addressed by Bohr's model. Another thing that we'll get into with Rutherford's model and its limitations is actually the emission and absorption spectra as well. So because Rutherford didn't specify where the electrons were, when electrons were losing or gaining energy, it kind of predicted that electrons could lose or gain any amount of energy at all, because they could be anywhere within the atom. However, what we actually observed was that electrons could only emit and absorb certain amounts of energy, not just kind of like any amount at all. It would be a certain amount, right? And this is when we get into emission and absorption spectra, which we'll get into later. So that was kind of the other limitation with Rutherford's model. Now let's get into the Bohr model. So Bohr proposed that electrons only radiate energy in exact quanta or definite amounts of energy. And so as electrons radiate energy, they move inward towards the nucleus in definite quantum orbitals until a stable orbital is reached. So given this information, I'd like you guys to pause the recording and have a think about how the Bohr model addresses the issues of the Rutherford model. Right? Pause the recording, have a think about it, try to remember it from your notes, or try to kind of guess if you haven't learned this in class yet. So, let's talk about how it addresses the issues. Firstly, if each electron releases or absorbs a certain amount of energy every time it moves, and it kind of releases energy it releases energy in discrete amounts until it reaches a stable orbital. This tells us that we have kind of distinct, discrete orbitals, whereas Rutherford's model just kind of said that we had electrons going around anywhere. Bohr's model tells us that we have discrete orbitals that electrons can be in, but they can't be in between. So, if we have an electron moving down an orbital, it's going to emit energy because it's losing energy, right? And because the electron has moved down a certain amount, it's going to emit a certain amount of energy, which is relative to the difference in energy between the orbitals, right? So the absorption of a photon with energy equal to the difference in energy between an electron's stationary state and excitation energy state will cause the incident electron to move to the excitation state. So if we give an electron a photon that has the energy that it needs to move up an energy state or move up an orbital, it will. Every change in electron orbit corresponds to the absorption or emission of electromagnetic radiation. So absorption is when it moves up an orbital, or emission is when it moves down an orbital. So if the electromagnetic radiation is high enough energy, it will knock off the electron ionizing the atom. So the limit is the ionizing energy, right? So if we give an electron a bunch of energy, it will have enough energy to actually jump out of the atom altogether. And this is what we saw with the photoelectric effect, right? We saw if we gave the electrons enough energy, they would just jump off the atoms altogether and create a photocurrent. Alright, so now let's get into the emission and absorption spectra, which is what I was talking about before. So, as I said, the Bohr model tells us that the orbitals of electrons cause the emission and absorption of photons of definite and specific energy levels. And we know that this is related to the frequency of the light emitted or absorbed. So, The emission of energy and jump back down orbitals is stepwise, which means it occurs in chunks, right? A way to visualize this is being on a bookshelf. If each shelf is an energy state, a book can never be in between shelves. It can either be on one shelf or on another shelf, right? So, we can see the frequency of light emitted and absorbed if we run it through a prism spectrometer. And what we see is that the absorption and emission values are equal and opposite. So, the frequencies of light that a electron will emit are opposite to the frequencies of light which an electron will absorb. However, Rutherford's model predicted a continuous spectrum, right, where any frequency was emitted or absorbed. But of course, this is not what we saw. We saw discrete and definite amounts. All right, getting on to the Balmer series. So Balmer determined the mathematical relationship between the light colors emitted by excited hydrogen gas atoms. So we have a formula for determining the relationship between the wavelength and the number, the final and initial number. So Bohr determined the orbits for the hydrogen atom electrons based on the wavelengths for the spectral lines. Right? So, we also have de Broglie's justification of the Bohr model. So this applied the theory of wave-particle duality to the Bohr model of the atom, and this allowed the explanation of why only certain orbits are facilitated in the atom. So the circumference of the orbit must be an integral multiple of the electron wavelength. What this essentially means is it must be a whole number. Remember, an integral is a whole number. So this gives the below formula: n times wavelength equals 2 pi r. So remember, the 2 pi r, just like from regular maths, is equal to circumference. So n must be an integral, or like a whole positive number. And then the electron wavelength is given by our symbol there. So of course we have an integral multiple of the wavelength is equal to the circumference 2 pi r. Alright, so something as well that you can take from this, and this is also one of the principles of Bohr's model, although I guess it's not something that we typically focus on a lot because the concepts we don't learn about too much in year 12, but that is that the angular velocity of the electrons is discrete. Right? So this is a little bit of what de Broglie was talking about here.